Okay, now you know the different types of controllers or combinations, and what is the effect of each and every individual controller, and what is the effect of combination of the controllers, now which will improve transient state and which will improve steady state, which will improve both, and you know everything. Okay, so how the questions are asked in the GATE examination in the controllers topic. Okay, now we'll see. Okay, so I just explained one problem now which will cover almost all the questions, how the questions are formed in the GATE examination and how to answer and how to simplify that. Okay, then everything we can see in this particular question. Okay, so this is very important. Now the question what he is saying is, by considering the block diagram, he is giving the block diagram. Okay, so this is the block diagram. First we'll take the block diagram. Now that is the reason why I am just saying practical circuits. So if you understand the practical circuit, then this will be very easy problem for you. So this diagram which is already given in the question itself. Now what type of questions he is asking with this particular block diagram? Right, now this is the given diagram. Now just first I will explain what is the questions what he is asking. Okay, now he is asking question number 1. What is question number 1? Question number 1 is the dashed line box shown in the figure shown in the diagram belongs to which controller, which type of controller. Now first you observe the questions. Okay, so this dashed line box, now one box is given and one circuit is there in this box, and that dashed line box belongs to which type of controller. That is question number 1. Now what is the question number 2 he is asking? The question number 2 is determine controller constants. Determine controller constant values. This is the second question. And the very important one, question number 3 is determine all time domain specifications. Determine all time domain specifications. See, this question which will cover almost everything. Okay, so this box is which type of controller, and what are the controller, and what are the controller constant, and the third one is By using this block diagram, determine all the time domain specifications. All the time domain specification means rise time, peak time, delay time, peak overshoot, time constant, settling time, everything, everything. Okay. These are the questions. First, you note down the question first. Okay. Now we'll answer one by one question. Okay. Now first we will take the dashed line box separately and we'll do it. Okay. So now I want to first try to finish the first question. Now question number 1 first I want to do it. Okay. Now what is the question number 1? The dashed line box. This is the dashed line box. Now let us assume this is Vi of t. This is R. This is also R because same 1 kilo ohm, 1 kilo ohm, and this is C. Let us assume, okay, R, C. Later we will replace the constants, okay, don't worry. Okay. Now this is V naught of t. So then if I want to find the transfer function first, because this is in S domain, therefore I want to find the transfer function. Now what is the transfer function? Laplace transformation of output V naught of t is V naught of S, Vi of t is Vi of S, Laplace transformation of R is R is R, C is 1 by SC. Now you find the transfer function first. What is the transfer function? Now the transfer function V naught of S by Vi of S, which is equal to minus Z2 of S by Z1 of S, which is equal to minus, what is Z2 of S? R plus 1 by SC by, now what is Z1 of S? This is Z1 of R into gain minus 1. So minus R. So minus minus cancel, 1 plus SCR by SCR, which is equal to 1 plus 1 by SCR. So now what is the transfer function? This is the transfer function. Now the transfer function Laplace transformation of output by Laplace transformation of input, which is nothing but 1 plus 1 by S. Now we replace the values. What is the values? R and C values are given now. R equal to 1 kilo ohm, R equal to 1 kilo ohm, C equal to 1 microfarad. And therefore C is 1 microfarad 10 power minus 6, R is 1 kilo ohm 10 power 3. So which is nothing but 1 plus 1 by S into 10 power minus 3, which is equal to 1 plus 10 power 3 by S, which is equal to 1 plus 1000 by S. So finally what is the transfer function? Finally the transfer function is now 1 plus 1 by S into 1000. Am I not? Now what is this? 1 plus 1 by S into 1000, or you may write like this also. Okay, it's not a problem. Okay, S plus 1000 by S. So you can immediately get the answer. One pole at origin. So one pole at origin means definitely that is belongs to I controller, and one finite 0. one pole at origin and finite 0. Which controller? You tell me which controller it is. So, and this is the one pole at origin and one finite 0. Therefore, which controller it is? Therefore, this dashed line box. Now, what is the question number 1 answer? The dashed line box belongs to PI controller, proportional plus integral controller. This is question number 1 answer. The dashed line box shown in the block diagram belongs to PI controller. Am I not? And what is the question number 1? What is question number 2? Now the question number 2 is determine controller constant. Determine controller constants. Now you tell me what are the controller constants. This is the transfer function. But what is the transfer function? Now the transfer function, which is nothing but Kp plus Ki by S, or which is equal to Kp into S plus Ki by S. Compare. You compare and find what are the determine the controller constant. Now the controller constants are, while you are comparing, the controller constant Kp, which is equal to 1, Ki, which is equal to 1000. Now this is the controller constant, Kp equal to 1, Ki equal to 1000. This is the question number 2. Determine the controller constant. Okay. Now first you finish these 2 questions and we will see the last question. Okay. Third question in the same. Clear or not? Okay. Now this is very, very important. Okay. Now students, then this is the PI controller and this is the PI controller constant, proportional controller constant and integral controller constant, proportional controller gain or integral controller gain. Okay. Now see here. Now we will go to the question number 3. What is the question number 3? Determine all the time domain specifications. So determine all the time domain specifications. So then this is the actual system or plant. Practically this is called as a plant. So this is the controller. Now what is the controller and which type of a controller it is? Now this controller is nothing but, which we already find, this is a PI controller. How much you are getting? S plus 1000 by S. Now this is the controller. This is the PI controller. Then now this PI controller is working on the plant. This is the PI controller is going and working on the plant. Am I not? So this is nothing but a PI controller. Now we will see with PI controller. Same. With PI controller, then what is the overall open loop transfer function? Tell me now. With PI controller, the open loop forward path gain, open loop control system transfer function G of S, which is equal to S plus 1000 by S into 1 by S plus 1 into S plus 1000. Now S plus 1000 cancel, which is equal to 1 by S into S plus 1. Now this is the open loop control system transfer function. Then what is the characteristic equation? Because time domain specifications are related to the closed loop control system. 1 plus G of S equal to 0. Therefore, S into S plus 1 equal to 0. S square plus S plus 1 equal to 0. This is the characteristic equation of order 2. Then if you find the roots, what are the roots? Now these are the characteristic equation of 2 roots are minus b plus or minus square root of b square minus 2a. Minus b plus or minus square root of b square minus 4ac by 2a. Now this is the 2 closed loop poles. So there are 2 closed loop poles. Then once the closed loop pole location is available, then we can find any characteristics or any parameters or whatever it may be, right? So now we'll see. These are the poles location. complex conjugate poles. Now this is plus j root 3 by 2 minus j root 3 by 2. Now this is minus 1 by 2. Now you can easily find all the parameters. The poles which lies on left hand side of S-plane, system is stable and order equal to 2. And when the complex conjugate pole means this is nothing but underdamped response. This is the underdamped response when damping factor zeta less than 1 greater than 0. So when this is the underdamped response, then the complex conjugate poles from the origin, if I draw a vector line to this complex conjugate pole, will make some angle of inclination. Now this is called as theta. Therefore now see here, if I just take this right angle triangle separately, now what about this adjacent distance is zeta omega n, which is nothing but 1 by 2. Now what about this side distance? This side distance is nothing but omega d, which is equal to directly 4 radians per second. This is omega d, which is equal to 4 radians per second. Now this is 4, this is 1 by 2. Then what about this distance? You just see here. Oh, sorry. This is root 3 by 2. Sorry. This is root 3 by 2. Omega d is, this distance is root 3 by 2 directly. Now what about this hypotenuse distance? Square root of 1 by 4 plus 3 by 4. So square root of 4 by 4, which is equal to root 1, which is equal to 1. So this hypotenuse distance is nothing but directly the natural frequency of oscillation, 1 radians per second. Now you can find every parameter, am I right or not? So now what is the cos angle of inclination theta adjacent by hypotenuse, which is nothing but 1 by 2. But this is nothing but actually a damping factor zeta. How much is less than 1? You can get the same answer. And from here we can write that theta, which is equal to cos inverse of 0.5. Now what is the rise time TR? Rise time TR, which is nothing but pi minus theta by omega d, which is nothing but pi minus theta is cos inverse of 0.5. Omega d is already calculated, root 3 by 2. This is rise time. Now what is the peak time? Peak time, which is nothing but n pi by omega d, where n is 1 by default, pi by omega d is root 3 by 2 seconds. Now delay time. This is the delay time is approximately 1 plus 0.7 zeta by omega n, which is equal to 1 plus 0.7 zeta is 0.5 by omega n is 1 seconds. This is the rise time, peak time, delay time, and peak overshoot. E power minus zeta n pi by square root of 1 minus zeta square. So e power minus zeta is 1, sorry, zeta is 0.5, n is 1 into pi by square root of 1 minus 0.5 square. Then this is the peak overshoot expressed in terms of percentage. And what is the time constant? Time constant also you can easily find, because a time constant equal to negative of reciprocal of real part, which is equal to 2 seconds. Once the time constant is available, you can find all the parameters, right? You can find settling time. What is the settling time? The settling time Ts, which is equal to phi time constant. So phi time constant is 2 seconds. So 10 seconds for 0% error. time constant is equal to 3 time constants, means 3 into 2, 6 seconds for 5% error. The settling time Ts, which is equal to 4 time constant, 4 into 2, 8 seconds for 2% error. Now, because time constant here is 2 seconds. This is the settling time, peak time, rise time, delay time, peak overshoot, all the time domain specifications available. Once if you know the closed loop poles location, you can easily find everything, okay? But in one GATE examination question, not all, but I just give in one question such that he may ask anything, okay? He may ask only peak time, or he may ask what is the controller constant, or what is the, which type of a controller, and what is the controller gain, right? Or what is the peak time, delay time, raise time, time constant, like the individual questions may be also asked, okay? Note down this. Okay, so this is a controllers topic, okay, which is very useful, and n number of objective questions you can form from this particular controllers topic, and which is very useful in all the competitive examinations, including the GATE examination. Right. But actually I just put the topic of controllers and compensators, okay. So we finished the controllers, right? We finished the controllers, then we will try to go for the compensators topic, okay. So now you already have an experience of, in controllers we have an experience that one pole at origin, one simple pole and two simple poles, or one finite zeros, am I not? In a controllers, that controller will produce some poles or some zeros, some poles at origin, some zeros at origin, and you know the effect of pole at origin, zeros at origin, finite zero, two finite zero, one finite zero and one pole at origin, like that you know all the combinations, am I not? So that poles and zeros are which will try to improve the system performance, which means that it may improve the transient state behavior or it may improve the steady state behavior. Now similarly, now this is the compensator. Now this is the compensator. This compensator is a circuit. This is the compensator is a circuit produces a finite poles and a finite zeros. Produces a finite pole and a finite zeros. Finite, the word finite means the poles and zeros must and should lie on left hand side of a plane. Now this compensator produces a finite poles and finite zeros. Then by using those finite poles and finite zeros, we will improve the system performance. So what is the meaning of that? We will improve the system performance means what? So we will improve the system performance means it improves the stability, or it may improves the error, or it decreases the error, or it increases the system stability, or it decreases the system stability. So these finite poles and zeros are useful to you to improve the transient state behavior or a steady state behavior. First of all, I require a finite poles and finite zeros. That finite poles and finite zeros are produced by using an electrical circuit. That electrical circuit is named as a compensator circuit. Okay. So we want to identify here, sir, then if this compensator produces a leading phase or this compensator produces a lagging phase, or this compensator produces a leading phase, then this is called as a lead compensator. If this compensator produces a lagging phase, then that is called as a lag compensator, like that. So it should have two features. What is the two features? First of all, a compensator is a circuit which is used to produce a finite poles and finite zeros, and second is this compensator is a circuit, if it is producing leading phase, is a lead compensator, producing a lagging phase, then it is said to be a lag compensator. Clear or not? Okay, note down. A compensator is a network, is a circuit which produces a finite poles and a finite zeros in the left hand side of S plane. Okay, a compensator is a circuit which produces a finite poles and a finite zeros. Finite itself is the left hand side of S plane. Using these finite poles and finite zeros, we will try to improve the transient state analysis or a steady state analysis according to your desired characteristics you can achieve with this. Okay, if it is poles and zeros are in such a fashion it is arranged and produces a leading phase, that is a lead compensator. These finite poles and zeros are arranged in such a fashion to generate a lagging phase, then it is called as a lag compensator. Okay, note down. Okay, now we'll see first. Now first we will see this is a compensator or not, because compensator is a circuit is producing some poles and zeros. Then he is giving one circuit. Now this is the circuit which is given to you. Now this is the compensator circuit, right? Now first we want to simplify this circuit and we will try to do the analysis. Okay. Now Laplace transformation of V naught of t is V naught of S. Laplace transformation of Vi of t is Vi of S. Laplace transformation of R1 is R1. Laplace transformation of C1 is 1 by SC1. Laplace transformation of R2 is R2. Now what is the transfer function? Now Laplace transformation of output. Now that resistance, voltage across this resistance, that resistance by the total resistance R2 plus R1 parallel with 1 by SC1 into the supply voltage Vi of S. What is the transfer function? Now the transfer function V naught of S by Vi of S, which is equal to R2 into 1 plus SC1 R1 by R2 plus R1 plus R2 SC1 R1. Okay. Now this is a transfer function of the given electrical circuit. Okay. So in the denominator, can I take R1 plus R2 as a common? So in the denominator, if I take R1 plus R2 as a common, V naught of S by Vi of S, which is nothing but R2 by R1 plus R2 as a common, 1 plus SC1 R1 divided by 1 plus R2 by R1 plus R2 into SC1 R1. Now this is the transfer function. So if you observe here, now that is the transfer function. Now can I write like this? Now this is the time constant which is R1 C1. This is the lead, he is saying some compensator. Let us assume this may be a lead compensator. So he is saying that this compensator is a lead compensator. We will verify that, okay? We will verify. So if this is a lead compensator really, therefore this is called as lead time constant. This is the lead time constant. Now tau equal to R1 C1, lead time constant. And this is the compensator constant alpha, which is equal to R2 divided by R1 plus R2. Now this constant which is less than 1 because denominator value is more. Therefore this is called as a lead time constant. Now this is called as lead compensator constant. Lead compensator constant alpha, which is equal to R2 by R1 plus R2, which is less than 1. So these are the time constant and compensator constant are the compensator parameters. Compensator parameters which will give compensator parameters which will give compensator characteristics. Like a system gain and time constant. Now can I replace here? Yes. Now see the transfer function. Now finally the transfer function V naught of S by Vi of S, which is equal to alpha into 1 plus tau S by 1 plus alpha tau S. Right? Now this is the transfer function. Now this is the transfer function V naught of S by Vi of S, which is equal to alpha into 1 plus tau S by 1 plus alpha tau S. Now this is finally the transfer function. But what I am saying, the time constant and compensator constant are the compensator parameters which will give the compensator characteristics which is similar to the poles. Now how the closed loop poles will give all the characteristics, in the same manner the compensator parameters are the compensator time constant and a compensator constant which will give the compensator characteristics which is a function of poles and zeros location. So these are always this parameters should be function of poles and zeros. It should be only a function of poles and zeros. This parameter should be a function of poles and zeros. So the time constant and compensator constant must be a function of poles and zeros. Therefore, this is not the compensator parameters. this is some attenuation factor. This is some attenuation factor which will create some distortion. Therefore, it is also called as distortion factor because our characteristics are disturbed. So I don't want to keep this attenuation factor. I don't want to keep this distortion factor. We want to suppress that attenuation factor. So can I suppress this attenuation factor? Can I suppress this distortion factor? Yes. So we can suppress this attenuation factor. We can suppress this distortion factor by passing this compensator through an amplifier. Design an amplifier of gain which is reciprocal of that suppressed factor such that this alpha and this alpha is cancelled, this distortion factor is cancelled. Now this the transfer function is V0 of S by Vi of S, which is equal to 1 plus tau S by 1 plus alpha tau S. Okay. Now this is the finally the transfer function without any attenuation. But one disadvantage with this, so our circuit cost and complexity increases because we want to use an extra hardware which is called as an amplifier. So our cost and complexity is increased. So this is somewhat disadvantage of this particular lead compensator. Okay. So what is a finite pole? What is a finite zero? Finite zero is minus 1 by tau. Finite pole is minus 1 by alpha tau. So let us take minus 1 by 1 which is equal to minus 1, minus 1 by 1 into t, time constant. So this is less than 1, so 0.1 which is equal to minus 10. Because here I am taking one example. In this example, alpha I just take 0.1 which is less than 1 and time constant tau which is equal to 1 second, for example, because this is a lead compensator, alpha is less than 1, so I just take less than 1. Okay. So this is the minus 1 by 1, minus 1 by 0.1 which is equal to 10. So you can easily identify that. What is the pole zero location in S-plane? Now this is the S-plane. First one is finite zero, minus 1 by tau. This value for easy identification. Okay, easy to locate with the values. So and next one is finite pole, minus 1 by alpha tau. So the lead compensator produces finite zero and a finite pole in the left hand side of S-plane. Now this is the lead compensator. So first of all, this is the compensator. What is a compensator? First feature, compensator is a network which will produce a finite zero and a finite pole in the left hand side of S-plane. Yes, this is a compensator. So this circuit is nothing but definitely a compensator circuit. But now I want to observe that whether this compensator is a lead compensator or not. Only this part is doubt, but this part is clear. Compensator is a device. Compensator is a network which will produces the finite pole and a finite zeros. And that finite poles and finite zeros we can add it in the circuit in a cascading or in a parallel combination, in a series combination, and we will try to improve the performance of the system. Understand or not? Okay. Now first you note down this, that this is a compensator of a lead, produces the finite poles and finite zeros, and after that we will see really this compensator circuit will act as a lead compensator or not.